Mohanty sir, shall we start because it is already 9:30 and many of them have
Yes.
joined the YouTube live streaming. Okay, sir.
Okay.
Okay, so
Sure.
so let me introduce sir you for because today there may be a different set of participants.
Sure.
Okay,
Sure.
okay. Uh, Good morning, all of you. My name is Dr. Amit Joshi, and I will serve as a moderator for this particular session. So today we have a Professor Sarju Mohanty as an expert. So Professor Mohanty has received his bachelor degree with honors in electrical engineering from Orissa University of Agriculture and Technology, Bhubaneswar in 1995, master degree in system science and automation from the IISc Bangalore in 1999, and PhD degree in computer science department from University of South Florida in 2003. He is currently professor at University of North Texas. His research is in smart electronic system, which has been funded by National Science Foundation, Semiconductor Research Corporation, US Air Force, IUSSTF, and Mission Innovation. He has authored more than 350 research articles, 4 books, and invented 4 US patents. His Google Scholar H index is 36, I10 index is 134 with more than 5,800 citations. He introduced the secure digital camera in 2004 with built-in security feature designed using hardware assisted security or secure by design principle. He is widely credited as the designer of the first digital watermarking chip in 2004 and first the low power digital watermarking chip in 2006. He is a recipient of 12 Best Paper Award, Flight Specialist Award in 2020, IEEE Consumer Electronics Society Outstanding Service Award in 2020, and IEEE CS TCVLSI Distinguished Leadership Award in 2018, and P. Rose Award for a Best Book Chapter in Physical Science and Mathematical category in 2016. He has delivered 9 keynotes and served as 5 panelists at various international conferences. He has been serving on an editor board of various peer-reviewed international journals like IEEE Transaction on Consumer Electronics, IEEE Transaction on Big Data. He is editor-in-chief of IEEE Consumer Electronics magazine. He has been serving on as a BOG of IEEE Consumer Electronics Society and has served as a chair of Technical Committee of TCVLSI and IEEE Computer Society during 2014 to 2018. He is the founding steering committee chair of IEEE International Symposium of Smart Electronic System, steering committee and vice chair of IEEE CS Symposium on ISVLSI, and steering committee vice chair of OITS International Conference on Information Technology. He has mentored 2 postdoctoral researchers and supervised 12 PhD dissertations, 26 MS theses, and 10 undergraduate projects. Thank you, sir, for accepting our invitation. It's our honor to have you over here. Now I request sir to proceed with the session. Thank you, sir.
Good morning, everybody. Thank you, Amit, for the kind introduction. And I'm really proud to be part of MNIT, this effort that is going on every year. In fact, I really wanted to go in person. Okay, I like to travel, right? Anyway, so because of obvious reason, we are meeting electronically, and I hope you will find all these slides that I have are educating for you and for the audience. So what we'll talk here today is a concept that is called security by design or secure by design. Okay, and I will present that in the context of cyber physical systems. So the outline of talk is like this. We'll discuss what is cyber physical system. It's a component on smart cities. That is how I'll propose as a top-down view. Then the security challenges cyber physical systems typical face. There are a variety of them, starting from agriculture cyber physical system, medical or healthcare cyber physical system, energy, and so on. Then what are the drawbacks of existing security solutions? And we'll discuss about the paradigm that we call secure by design or security by design. And the predecessor of it or a subset of it is hardware assisted security that also we will be discussing, and conclusion and future direction. And after, so we'll have the discussion first, and after that question answer session. So feel free to note down the questions that you can ask me later on. So I start with the big picture of things. This is the motivation I always present, that is urban migration, that is population in most of the countries are going towards urban, and it is a little bit alarming that by 2050 what is projected that 70% of world population will be urban. Okay, so as a result, the resources will be overwhelmed. Limited resources are there, starting from living space to healthcare resource and so on, energy and so on. So how do we ensure the smart city sustains, okay, while accommodating such a large population? And also, while smart city was getting a lot of attention for last 5-10 years, in fact, in India also a lot of initiatives are going on. Then another concept called smart village also has started, and IEEE is playing a major role in standardizing smart city, so as smart villages. And in some context, smart state and smart country, for example, Singapore is a smart country that can be envisioned. What makes city smart? What I call as 3 I's, that is instrumentation, interconnection, and intelligence. So a lot of controllers, actuators, and sensors, all these are there. Okay, they are essentially ears and eyes of the smart city. So they are getting data, sensing things, and also helping to control things. And all the devices that sensors, in addition to computing units and so on, they are connected. Interconnection is the important part. And then the data that we gather, we process through AI techniques, machine learning techniques, and so on. And as a result, we are able to make decisions. So these 3 I's essentially come from what is called Internet of Things. Internet of Things is not internet. Okay, so internet was there. Okay, so Internet of Things originated when something other than computers got connected to the internet. Okay, and as far as I remember, what is the first thing that was connected to the internet other than a computer is a toaster machine. Okay, so anyway, so Internet of Things essentially is the we can say is the workhorse behind the smart cities. So this is the vision that we can say is what is IoT. If somebody asks, this is the answer. Okay, it's one model, we can say, but there can be different models. So we have things. Okay, so things are not just sensors or actuators. What is important there? They have connectivity capability, IP address. Okay, and then comes the next layer with various type of local area network, body area network for Internet of Medical Things, personal area network, and for vehicular, that is transportation, CPS, we have control area network. All these things come to picture. Then cloud service, of course, and then various applications are built at the top of all these things. So we can envision IoT is a configurable dynamic global network of networks. Okay, so a lot of networks are there, they are connected. So it's a network of network, or we can say system of systems. Now, a specific example, yesterday we had a lot of discussion on Internet of Medical Things or healthcare cyber physical system. So a specific example of IoT is IOMT, Internet of Medical Things. So we have here a specific type of sensor, that is the sensor that goes to human beings for different measurements, whether it's blood pressure or glucose level and other things. Okay, so all these wearables, we can say implantable also, all these things, okay, they are connected through Bluetooth or through Wi-Fi, and then the data goes through a router and so on, and as a result, overall what we get, and there is then electronic health record, all these things, so overall what we get is Internet of Medical Things. And so this is a specific example. Another example is the industrial Internet of Things. So here the IoT is in the application of industrial manufacturing and so on. Okay, so industrial automation, then predictive maintenance, all these things are by the help of IoT, industrial Internet of Things. And similarly, actually, we can envision other things like Internet of agro things and Internet of energy for energy sector. Now, when we want to see that how IoT, CPS, and smart cities are together, they are essentially making same thing at the end. It's something, some physical entity like smart, like cities are made smart cities. Okay, so in a what you can say top down or bottom up view, in either way, we can say IoT makes CPS, CPS makes smart city, or other way around. Okay, smart cities are made up of cyber physical systems, and each cyber physical system has a physical entity and then cyber entity, which is the IoT. We can visualize that way. And example of a CPS is a healthcare CPS, agriculture CPS, energy CPS, and so on, or transportation CPS. All these are different examples. So that is how IoT and CPS are related. So this is the what you can say thought that I have given in 2016, but different people may have different things. That is, some researchers believe IoT and CPS are same. They have their own thoughts, so we can agree or disagree. But this is the vision that I have given in the July 2016 article, and this article is considered as one stop reading for smart cities. Very well cited, and thousands, tens of thousands of reading there in IEEE Explore. Now, when I was doing a little bit more reading, that is CPS versus IoT, what I found, if I model like this, other researchers have given this model as well. That is what CPS consists of is a computation, communication, and control. Okay, cyber physical system. Now, then I go to IoT, and IoT also have more or less same things: connect, compute, and communicate. So when we see that is in 3 C's of IoT or 3 C's of CPS, they are more or less same. But as I said, this is a better view, I feel, because this is like IoT, CPS, and bigger cyber physical systems, which is smart city, are made possible through this. So this is the model that I believe. But some people think they are more or less same. Anyway, now an example of healthcare cyber physical system, example of a cyber physical system is healthcare cyber physical, or HCPS. We had 2 hours discussion yesterday on this, and you can see the video, or so you can see the slides. And here, what we're doing, the physical entities here like hospitals, ambulance, even medical devices, and so on. All these are made smart, and they're connected together. They're talking to each other, helping each other. Okay, with the help of Internet of Medical Things, and overall, they are creating what we call as HCPS, or healthcare cyber physical system. Another example of CPS is energy cyber physical system, or ECPS. So this is again a major thing. Okay, like healthcare, energy we need. We are talking to each other right now. I'm here and you are listening to me talk. Okay, energy is an important thing. Communication is an important thing. So energy CPS is like market value point of view. There's a significant thing here, and smart grid is an example of a ECPS, where we have a regular grid made smart, and overall is a part of ECPS that we're talking about. So we can see a little bit different model of same ECPS. In in the previous one, we had a big picture where we had smart grid. Now I go to the details, so we can have a smart grid. No doubt, before that we can have smart generation. Okay, thermal power plant, and then renewable. They are working in synchronization and generating. Then grid is taking power to different places. Okay, and so smart grid here. Then we can talk about smart storage, and this is what middle I have written. I like it very much. Is smart consumption. Okay, so energy, particularly electricity, is certain thing that is very much dependent on the consumption. Okay, so if user doesn't consume, generation should not be done, and if generation happens, rather there will be instability in the grid. Of course, one can say we can store, but storing is limited. Okay, storage battery is expensive as well. Okay, so in energy CPS point of view, we can say now smart grid, smart generation, smart storage, and importantly, as I said, smart consumption is coming to picture. So these are few examples I mentioned, okay, of CPS, and they are all made by corresponding Internet of Things. Okay, now what are the security challenges of cyber physical system that so various security challenges that we will see. This is a picture that we see all the time. Okay, this becomes big news that this database was hacked, that database was hacked. So these are cyber attacks, okay, happening. Okay, and I call them these are mostly IT security issues. Okay, not necessarily IoT security issues, but these affect a lot of people. That's why always becomes big news. Okay, so for example, some retail stores online site was hacked, or Yahoo's site is hacked, and ransomware. All these become big news because they affect a lot of people. Okay, but these are, as I said, are IT security issues. Now, IoT security, on the other hand, that is coming as we make more and more physical entities smart, okay, by integrating IoT, okay, whether you call it IoT, IoMT, or Internet of Agro things, all these variety of things are there. So in general, when we say IoT, we have previous slide I said IT. Here I am talking about IoT. So when we are integrating IoT in different physical systems, okay, so the security things are becoming much more challenging. Okay, for example, a hardware trojan is a security threat that can happen to different hardware. Then like side channel attack, again, this is a hardware related problem. And then a lot of people are already aware denial of service kind of attack that happens in a regular connectivity, that can happen as well with IoT. And there are many more, as you can see here, tons of them have been listed here, and many more basically keep evolving day to day time. So anyway, so these are the threats, and there are some solutions people are working, okay, and people, including many of you, must be working in this area. So a lot of solutions are there, okay, but solutions are always what you can say not foolproof. Okay, so that's why this is a competition between new threats coming and different solutions we give, which are better than what is existing, as well as that can address to new security threats. Okay, anyway, so this is IoT security, which is different from what we saw here is essentially IT security. Now, IoT security point of view, when I go to a little bit details, so that is, I look at the devices that we have. For example, medical device, RFID, pacemaker, insulin pump, then here, heart rate monitor, all this can be hacked. Okay, pacemaker particularly can be, if hacked, it's a life-threatening situation. Insulin pump as well. Similarly, home devices, okay, all these, when they're connected to the internet, they can be hacked. Okay, smart thermostat, all these things. And so phone and then other wearables here can be hacked. And similarly, business devices can be hacked as well. And here, transportation side, if they are hacked, those are again much more serious problems. So, for example, your autonomous car is hacked. Okay, those are serious problem, and so as a drone. Anyway, so these are different altogether kind of threat and much more serious, and so what you can say life-threatening threat that we'll see in our discussions. Now, when we want to, what you can say, study, okay, what are the threats we can say, we can, what you can say, group them as some are direct security threats, some are privacy aspect threats, some are ownership. Okay, so there are three different ways. So security are much more serious problem. For example, a hardware trojan is there, which is affecting the hardware security or the system security. Okay, that can basically cause a serious problem. Let's say hardware is part of a smart grid, or a hardware is part of a car, and there is trojan. Okay, so those are serious problems. Okay, privacy also, a lot of people care for privacy. For example, they don't want others to know where they are, or they don't want others to have access. So privacy in that respect is a problem. And then IP right, the intellectual property right, who owns something, some hardware, some software, okay, or some media. Okay, all these are IP, intellectual property rights problems. So these are three different groups, and severity point of view, security, I believe, is a serious, most serious, followed by privacy, followed by IP rights. Okay, so when I see a specific embedded device, so this is basically a black box view of embedded system, which has some ASIC, okay, DSP kind of, then some embedded processor, like, okay, general purpose, then some memory and so on, and then some operating system, okay, and applications are running at the top of it. And this embedded system is processing some information, generating certain information. And if you see this hypothetical system I have is the attacks are variety of types. Okay, that is starting from physical attack here, like side channel and so on. Then firmware attack can happen, and memory can be attacked. So if memory is attacked, system can be made dysfunctional, as well as data can be stolen. Then variety of network and other things that we are aware of that can happen. So this you can see here, like in with the help of a hypothetical embedded device, how we are seeing that so many variety of security related and privacy and other related attacks can happen. Now this is a scenario where basically I'm showing that is how different variety of this is a basically energy CPS kind of situation where if power grid is attacked, okay, the situation is far serious. Okay, so that means you will be completely like big cities can be made completely powerless. So imagine that situation. Like if, right now, the way in a situation we are facing, like most of the people in the planet are kind of in stay at home, those kind of things. But at least we have power. But imagine if complete power failure happens by because of power grid attack. So those are much more serious problem actually. And then in the transportation CPS here, okay, that is if a smart car is hacked, that means somebody you think your car is driving itself because it is autonomous car, but somebody has taken over, okay, and then a slight change in the decision. Let's say you wanted to make a left turn, somebody takes over and makes a right turn, or you want to put a brake and somebody accelerates. So those kind of situations are very serious fatal situation that can happen. Similarly, drones are now becoming what you can say much more useful in like smart city applications, smart transportation also. For example, some companies are trying to deliver their items, okay, to the doorsteps with the help of drones. So if they are hacked, then there are serious consequences. So anyway, so these are much more serious problem I consider. Okay, these are the security of the cyber physical system. Okay, and much more serious consequences compared to IT security and so on that we are already aware. So a specific example of a privacy of a system. Okay, why privacy of system is that important? Okay, so as I said, security, the way I showed in the previous slide, are much more significant, but privacy also important. For example, if somebody knows what are the components that your smart car has, potentially he or she can, a hacker can what you can say, make ideas or get better ideas how he or she can hack your system. Okay, so system privacy can be exploited to make security attacks eventually. Then location privacy. Okay, you are in autonomous car, things are connected to GPS and it's driving itself. So others can basically find out where you are. So that is a location privacy. Similarly, one can say personal privacy. Okay, so that is why somebody should know that is what are your physical or physiological data and so on. Okay, so that's the personal privacy aspect. Okay. Now, when we see a specific CPS, for example, a smart healthcare CPS, that is healthcare CPS, okay, HCPS. So we have data aspect, okay, that is like everybody is worried to keep their data, healthcare data in particular, in confidential, nobody should know, and those aspects. And some people should have only access to it. For example, your primary care practitioner or your like a technician, that means who is doing X-ray, those kind of healthcare technicians. And then like device security, for example, you have pacemaker, only a doctor, whenever doctor wants to configure it, can have access, not others. So device security and other aspects are also there important in the HCPS. Now, here we saw that is in a bigger scale, that is how a power plant, car, and other things, security can be a problem. And here in the healthcare domain, that is devices, for example, wearables can be problems. And these are practical things. That's why I quote some newspapers. Okay, that is 2019 insulin pump was hacked, and FDA issued warning so that people are aware. And similarly, here, other examples what we have seen is pacemaker, like Medtronic pacemaker here, okay, has Wi-Fi connectivity and it is connecting to the servers. As per the news here, users are not aware that their pacemaker is connected to the internet. Okay, so those kind of warnings FDA gave, so these are scary. That means imagine you are part of the internet and somebody else can potentially access your implantable devices or wearable devices. Okay, and a hacker can drain your battery completely, can change the insulin doses. Let us say you are diabetic, and as a result, you are putting an insulin pump, and then the insulin doses can be controlled by somebody without authorization and so on. So that those are scary situations that practical people have seen, and these are much more serious, I consider. Okay, so this is an example hacking happened. Okay, this is a pacemaker and also other implantable are there. And here, what happens the RF connectivity, because of that, these are connected to the server, and the hacker can anybody can hack Wi-Fi connection. Okay, so those are the problems. So that what is the negative consequence? I was just mentioning, a hacker can drain the battery. Okay, hacker can make it dysfunctional. So those are serious problems. So that in a cyber physical system, HCPS, we have to worry not just the electronic health record and so on, but the device security. Then if you see the IoT device or HCP devices, okay, can be attacked in many ways. So that means somebody can pretend as authorized. For example, let's say doctor wants to have access to control the doses or to configure the pacemaker and so on, and but it's essentially a hacker. And then reverse engineering is a problem I consider. Many medical devices are available like any other hardware, cheap. Okay, and similarly, I know even in the automotive market, okay, that is the transportation CPS, a lot of electronics are available which are basically cheap and they may not do the function well or may not be safe. So anyway, so these are the things that and more can happen. Okay, and these devices need to be protected from those attacks. Now, so we discussed a few things which are healthcare CPS. Now, when we talk about the eCPS and ACPS or smart grid, okay, so grid and they become smart grid. So a lot of that's different software and other components. So SCADA system is here, a software component, and then there are different PLCs and so on. So the different embedded devices can be there, and as a result. And they are connected to internet, they are controlling the power plant. Okay, so this is the control room, and these are generation system, distribution system, and so on. And even meters. Okay, so all these are now connected, and as a result, attack can happen in any layer, and as a result, the whole system may have instability and so on, and complete failure even potential possible. There are examples we will see. And when we hierarchically see the situation, consumption, distribution, transmission, and generation, there are different local area network. For example, here it's home area network, here neighboring area network, wide area network. So intrusions can happen in any of these network point of view, like denial of service and other things you have seen. But other hacker needs to find a door somewhere, okay, and any embedded system, okay, and any software, okay, can be basically a lead for the hacker to get into the system and create problems. So these are serious problems that we are looking at as a solution. Okay, so these are part of energy CPS. Now, these are some examples. That is how energy CPS can be can attack, and there's some have happened. And for example, Ukraine 2015 attack, then. Like here, Alabama 2006 attack, okay, and this is 2008 attack, and another place, so on. So these are examples. So I'm not talking just like that, like a theoretical point of view. These are practical. Okay, that is, and these are very serious. Okay, so for example, closing a power plant or closing completely taking down a grid are a serious implication to the overall city, even overall state. Okay, so these are much more serious, like security problems. Okay, healthcare I showed, then this is power, and similarly transportation than just the IT security point of view. Now, transportation point of view, this is an example of a smart car. So that means this is a transportation cyber physical system, or TCPS. And actually, Conjugatrix magazine, the latest issue is on transportation cyber physical system. And the next issue, that is the September issue, we are putting it on the healthcare cyber physical system. And some point after a couple of issues, I have a plan to do agriculture cyber physical system. So stay tuned to the Conjugatrix magazine. I typically put the table of content in my LinkedIn and Facebook, and you can have access to many things. So anyway, so this is here the secret aspect of the transportation cyber physical system. And this is an example where I'm talking about like the autonomous cars, which have hundreds of millions of lines of code, okay, in the electronic control units. These are issues. So different issues are there to control different things. For example, to put the brake, or to control the lights, or other things. Okay. So anyway, the hundreds of issues are there, the control units, and they have some embedded hardware and other things, and they can be attacked. Okay, like any other device through different mechanism, relay, replay, jamming, and so on. Okay, and those are a serious problem. For example, let us say somebody else has control to your autonomous car. You want your car on its own should have put a brake, and somebody is accelerating it. Okay, or somebody, your car on its own should have turned left. Somebody is making it turn right. So those are very serious consequences that one can think of. And here I envision this situation. Okay, this I borrowed from this picture from somewhere. And what is the situation here? That is, sensors, okay, are sensing things, and then states of different physical entities and so on. And then we here the system, autonomous car system, is making some machine learning and then making certain decisions and so on. Here the information part. Then it decides, let's say, for example, to put a brake or to take a turn. So this system, okay, that is the autonomous driving system, needs to tell the actuator, yes, put a brake now. Okay, but that is what should happen, okay, in a normal situation. But a hacker, let's say, sends signal so that the actuator doesn't get the signal from the sensor, from the actual sensor, rather gets the signal from the hacker. Okay, so this is a very serious problem, okay, that can happen, and this is a difficult problem. It's not that easy to solve, because let's say you want to put some encryption here or something. Okay, so it will take some time. Okay, so in this, what I've heard from experts, that is on the transportation domain, suppose we need to make certain decisions here, that is the connection or the communication between sensor and actuator for certain things for the car, then anything here should happen in the range of milliseconds time. Okay, so in the if the process here is more than millisecond, then there can be different decisions that is not good for the car. There can be serious consequences. So just by putting encryption and other things will not work. Okay, so that is a very, very difficult problem. So anyway, and people are definitely working. Now I discuss another thing. It's NFC. NFC, why? It's a very small denomination compared to what we have discussed here, which are much bigger things. Why just jump to NFC, then RFID and so on. Okay, so because these are part of different CPS mechanism. For example, here logistic management and so on. Okay, NFC is there. NFC also we are using for payment and so on. So they are part of there, and they are subjected to eavesdropping, relay attack, and other things. So if they are hacked, okay, in a smaller domain, okay, so they can create problems for the bigger things like here. So let's say physical access or transit and or ticketing, other things which are bigger part of bigger CPS. So this is a thing that also one needs to solve. There are some solutions, of course. Then RFID. RFID again is a small entity, but RFID again used extensively for many different applications in the CPS. So for example, in transportation CPS, in logistics, industrial IoT, and so on. All these NFC, RFID, all this can be used, and they can have serious attacks, and one needs to solve those as well. So for example, here we have shown RFID can be used for logistics, asset management, access control, payment, and so on. These are part of CPS. So anyway, so various forms of attack can happen. One needs to solve these as well. hardware are part of the CPS. Essentially, if we see what makes CPS, okay, CPS we discussed makes IoT makes CPS when working with the physical entity, and this IoT has different hardware, different softwares, okay, and then there are middleware, firmware, all these things are there, and all needs to be protected. Okay, software, a lot of things people have primarily worked when it's security means people think of, okay, protecting the operating system, protecting the network with a Wi-Fi password. Those are trivial things people try. But we have still security problems. That means they have not worked well. Okay, because a lot of things are not solved. Okay, so for example, hardware Trojan. So hardware Trojan, I present this. I put this diagram in my book in 2015, and a very simple diagram. What I explained, that is okay. You are happy. You have a cryptographic chip or a watermarking chip for different applications. But what happens? Let's say you think your data is here, and you get the binary goes here. You get binary here. Then very simple. Let's say somebody puts a multiplexer here and then puts a copper cable here. Okay, so that means input just goes to output through a multiplexer. Then in this output here, you can sometimes get protected signal, protected information, okay, or sometimes get unprotected information. So here a multiplexer here is serving as a Trojan. Okay, so your output may be just coming from the input. It's a binary, and you may not be aware. So this is a simple example how a simple design modification can create serious problems, and then this signal here can be used to compromise this overall security that this cryptographic processor could have provided. Okay, and then this can be exploited when this encryption chip is a part of bigger system. This can be used to exploit the security of the overall system. Okay, so that can be serious for the CPS. Now, encryption, like everybody thinks, okay, I mean, security means encryption, right? That is how it has been. Okay, so so how secure are the encryption? Okay, so analysis shows when encryption really started, okay, people thought it's quite secure. 128 bit theoretically can take like years and years. Okay, so one cannot break it, but that is not the case. People are able to break 128 bit, and that is what this community who does this research and provides us the security mechanism. What they are doing, they're essentially using longer keys, 256 bit, 512, 2000, something like that. People have been using. Okay, so what is the intention there? To make the brute force attacks difficult by increasing the key size, so that making guess takes quite a bit of time. That has been the approach. Okay, and we have been living with it. But there are other things that can be done and we need to do. That is what the research is needed. So anyway, so AES, we have been thinking it's secure, but by the help of side channel attack, which we do not do the brute force approach. That means we don't have to take years and use a lot of computational resource. Okay, we are smart. We do side channel attack. That means we listen to the device behavior. Okay, that is through acoustics, noise here, or we analyze the power, we analyze the computational time and other things, and in fact, even the radiation and other things people can do. And in the process, breaking encryption is not a matter of years, but a matter of hours. And I remember I borrowed this slide from another researcher, and he was mentioning that is with $100 kit, okay, they can break any encryption within an hour. Okay, that is how easy it is with the help of side channel attacks. Okay, and the side channel attack can be done with the help of what is called differential power analysis, okay, or correlation power analysis. Okay, so it's essentially you are monitoring the power with the help of an oscilloscope like kind of device, and we want to break the security here of this smart card. Okay, we don't have to break the encryption at all. We study its power profile and so on, and then we make guess, and we keep on converging to a right guess till we succeed by doing some statistical analysis and so on. So CP and DPA methods are there. Okay, and so when you compare which one is more effective, people can debate, but it seems like CPA is effective and faster. Okay, but either way, okay, so these methods are available that defeats the encryption without defeating the underneath algorithm, rather exploits the hardware implementation of it. Okay. Anyway, this is a important slide where I say that is when we're making things smart and putting a lot of hardware and software, okay, middleware, firmware, and so on, okay, because we want to integrate IoT and other embedded devices and so on. So these firmware, if we reverse engineer or we put a firmware which is not a good firmware, and so that can be easily hacked. So in the process, because of the security problem of the firmware, one can get control to the embedded system, and as a result to the overall cyber physical system. So this is a serious problem as well. Not just we have discussed software, a lot of people are doing. I discussed many hardware aspects so where security problem can happen, and firmware is also a equally important thing. For example, in transportation, CPS, and so on, a firmware or a smart grid, that is NLCPS, firmware hacking can be a serious problem. Okay. And memory as a component, though we just discussed previous slide, firmware, okay, memory can be attacked in many ways, and particularly, let's say, very simplistic thinking, okay, wherever data stays, if I can take that control of that, then I have access to all the data. That is a simple thinking, okay, that can be done, okay, and but in addition to that, memory can be hacked to take control over the whole system, the embedded system. Again, as a result, overall system where embedded processor is playing a small role. So, and just like we have seen network attack and so on. So here, similarly, like snooping attack, then splicing attack, all these replay attack, all these variety of things can happen for the memory. So, and this is one important thing that is coming, that is called AI security. AI is important. We starting from anything that has a smart component and so on. Okay, AI is playing a major role in the backend. Okay, AI or machine learning. Okay, and they are essential models. Okay, so models are generated from the data. Okay, and then those models help to make certain decisions, and as a result, the system is working on its own, autonomous. Okay, and smart. So if a model is bad, okay, then we have bad, if data is bad, we have bad model. Then so model also can be changed by hackers, data can be poisoned. Okay, all these are different problems. Okay, and those are AI security aspects that people are now worrying. Okay, particularly because of autonomous car. And here is an example that people are worried as an example of how AI security is critical. Let us say we have smart transportation, okay, or that autonomous car, and this stop should be labeled as a stop sign, okay, but a hacker labels this as a speed limit sign. Okay, so this is a problem. You can see this right side, okay, instead of the autonomous car identifying that as a stop, it identified that as a speed limit of something. So as a result, you can see the consequences of this wrong decision because of bad model. Okay, and this is a very important problem that is really hot in the security domain that people are trying to solve. Okay, anyway, so this problem is a serious problem that I'm envisioning for the cyber physical system in general. Will have for different application, not just transportation, also in the energy sector, smart grid, and so on. It can have serious consequences. Now, what are the drawbacks of existing security solutions? Okay, so there are, we know variety of security issues are there. Okay, confidentiality, then authentication problems and other security, and there are some solutions. Okay, people have been working. That is why it's not like one day we solve all the problems. So we have solved to a certain extent. Okay, authentication, for example, by using PUF, we have done quite a bit of these solutions, and in fact, a lot of people have done in the past public cryptography and other things, different types of solutions. Okay, but they have their own set of limitations, and that is why nothing is fully solved. So we keep on doing, and there is always ample scope, particularly the domain side discussed, they have ample scope to work. Now, when I differentiate IT security versus IoT security, okay, that small o in the middle makes a big difference. Okay, so a lot of security solutions as of now, okay, have been coming from the thought of IT. Okay, that is the problem. Okay, so if we want to solve IoT security from an IT point of view, okay, we have a problem there itself. Okay, so IoT security needs to be solved from a hardware perspective, from a system perspective, not from a IT or communication perspective, okay, or information perspective. Okay, so one of the major thing I see that is IT security point of view, the number of devices are relatively small compared to IoT. IoT are much more like 1,000x more variety of security. And another important problem is this one. IoT devices may not have, each one of them may not have computational power. Okay, so we have to do the security under assumption that the host may not have computational capability to run the security. So those are far bigger challenges. Okay, one I said variety of devices, okay, lot of devices, and devices may not have computational power. Okay, and then here much more life-threatening situations in the security breach that can happen. So that's why these are serious problem, IoT security or CPS security as compared to IT security. Now here, for example, in the wearable, let us say somebody is hacking the insulin pump, okay, and controlling the dosage here, okay, or somebody somewhere the physiological data that a sensor should get, somebody is misleading, okay, so those are serious problem. And these devices we are seeing has serious problem of battery and computational capability. They do not have luxury of battery life, they do not have serious computational capability. And much more serious problem is implantable. Okay, so let us say let's say this is a brain pacemaker or a heart pacemaker. All these have implantable point of view. They have limited battery life. Okay, I should have another slide. Okay, so this is an example here. This is implantable. This is wearable. Implantable in particular has serious battery problem. Okay, and at the same time, computational capability is very limited. So any security solution needs to take that into account. That is we have to have solution which doesn't consume a lot of battery, which is safer, and which is also size point of view and weight point of view are reasonable. So then only it can be solved. So now, to give you this exact example, like I was doing a lot of search, so that is how bad is the battery life, okay, of a pacemaker or a neurotransmitter. Okay, so I saw pacemaker doesn't have quite a bit of computational capability, okay, and it is a very reliable device, of course, it is life-saving for a lot of people, and it has a battery life of 10 years. And if now the new generation pacemakers, they are connected to Wi-Fi and connected to the internet, and as a result, if somebody hacks and drains the battery, it's a very serious problem. Okay, that is people have to go through different surgery to replace it, and those surgeries are risky procedures. Okay, similarly, this is a neurotransmitter, that is a brain pacemaker, and so on. So this has a battery life of 8 years, which is far more 2 years shorter than this. So all these have serious consequences if battery is drained and other things, and somebody unauthorizedly reconfiguring or doing some things. Okay, so these are difficult problems to solve compared to IT security. So we saw a medical situation. Now, if we go to transportation cyber physical system, so here latency is a very serious problem I consider, and that's why you can see here, like suppose you are traveling, okay, and you lost a road and you are changing a direction and so on. Like you can see in the current situation how much time GPS takes. Recalculating, it takes certain time, but you cannot expect let us say you wanted to take a left turn to a right turn, or you wanted to put a brake. I'm talking about a transportation CPS when car is driving itself. Okay, so then it can happen when I remember this kind of situation when you take a wrong turn or GPS is not showing the right direction. Our human intelligence comes and we make corrections. But autonomous car, if it does that, it's impractical to do. And so here in this process, what I'm trying to tell is in the transportation or autonomous car point of view, security is a much more serious problem, and security has to be foolproof. Okay, that is one. And the second, security mechanism needs to act in a latency constraint. That means in the order of millisecond, it needs to take a decision. Couple of seconds means car can basically hit another car or hit a road and other things. So those road barriers and so on. So those problems can happen. So latency constraint is serious here. And if you go to these aerial vehicles, okay, drones and so on, the problems are far difficult. Okay, they are. If we are talking about in the car case, millisecond. Imagine how fast decisions needs to be taken here. Security solution that needs to work much faster here, and these have again medical device we discussed. Okay, this can of course not that less battery life compared to a medical device. These are far bigger battery we can have, but battery is limited to the range of the drones. So if we consume battery by using security mechanisms, then the range of the drone gets reduced. So this is a very difficult trade-off in the UAV security between energy and latency. Okay, I was mentioning in the healthcare domain, energy is a primary constraint. In the transportation domain, latency is a primary constraint. In the UAV here, that is energy and latency both are important constraints. And in the smart grid security, I was trying to do the analysis. So that is probably smart grid because power is not a problem. We can use the power, but still people expect that is the embedded devices who are doing the security mechanism and other things for the smart grid where the security flaw can happen. People want, so those are essentially, it's not like you have embedded device, means it is ready to free to use as much power it wants, but to a certain extent we can use power as compared to the health and UAVs we saw. But still we want energy overhead to be less and communication latency, things should be fast reacting. Okay, we cannot, because if something is secure, we cannot expect it to take quite a bit of time and so on. And so in the smart grid domain, because there is bigger entities at stake, okay, that is whole city can be have power failure and other things. So or a state can have total power failure. So that's why these are far bigger things that one needs to worry about in the smart grid security point of view. And in the computer, IEEE Computer Magazine, last issue, we have a cyber security for smart grids. I was guest editing that we have very good articles on this area, okay, that is covering various security aspects of smart grid that I what you can say bring to your attention so that you can read those articles. And I discussed Bitcoin, blockchain a little bit here. So this is a component that is essentially being explored to be integrated anywhere, any CPS that we can talk about. And it is distributed, decentralized, those aspects are there. So I want to touch upon how, what are the, what you can say, problems that it can have. And as I said, it is being explored to use in almost everything. Okay, even though it came originally for Bitcoin, it probably inventor did not intend to be used in variety of things, but people then found that a lot of people paid attention. They are exploring to use it in everywhere, not just cryptocurrency, healthcare, finance, service, property, and so on. Everywhere people are trying to use, whereas it was never meant to use that. So these are the things that needs to be solved, overcome for the blockchain before it can be used. It has high energy demand, it doesn't scale well, and it takes a lot of time, doesn't have privacy, and that is on-chain storage capacity limited. A lot of problems are there. People are trying, and 51% attack is also there. I think last year at least Bitcoin was hacked 2 times. Okay, and the 51% attack was responsible for it. So all this needs to be solved for blockchain to find useful in the application that people are thinking. So energy point of view, I discussed this, that blockchain original with proof of work was not meant to be used like this, that the way people are thinking. Okay, so as an example, a Bitcoin transaction is 80,000 times more power consuming than a credit card transaction. Okay, so it's a lot of energy usage. Similarly, mining a Bitcoin is a lot of money as well. Okay, it's energy equivalent of 2 years US household energy consumption. It's a lot of money. So, so security point of view, the blockchain has a lot of issues. Okay, like 51% data, for example. Okay, and other things that it can have. Similarly, privacy issues also. People think blockchain they are using, everything is hidden. Answer is no. Blockchain has serious privacy issues. Okay, for example, Bitcoin has no privacy aspect here at all. Okay, and these are different cryptocurrencies, and slowly different new cryptocurrencies are adding privacy aspects. But it's as you can see here, its privacy is seriously compromised with this. And similarly, smart contract is an example of blockchain. Okay, it has its own set of problems, and smart contract is implemented Ethereum and other different Nero, I think, another implementation. So it has serious vulnerability issues that people have found. So anyway, so you can see here that this blockchain, which can be, which is rather, I would say, is part of a lot of variety of IoT or CPS, because everybody is trying as if blockchain is solution for everything. Okay, so you can read a lot of articles that in my website. In fact, recently in the IEEE Computer, one blockchain article we wrote, IEEE Computer magazine, that is blockchain, how good or bad it is for healthcare applications. So you can read that. You will see we have discussed it's blockchain is easier to use, difficult to use in healthcare. That is the point, and we have a very good different discussions in that. It's not straightforward to use blockchain for anything that we just think the way people are trying. Okay. Anyway, and so those attacks that we see, we saw various types of CPS. Okay, can come from software and hardware resources, and software is quite common. Okay, people attack the systems remotely through software, and we know denial of service, then password-based attacks, spoofing attack, all these things happens. But I want to bring your attention to hardware-based attacks. Hardwares are much more serious and very difficult to find out. Okay, for example, Trojan. Okay, so a Trojan is existing at, I gave an example, very small hardware modification that may exist, but people cannot easily find that. Okay, unlike software. Okay, and those are very serious and very difficult attacks, and this is where the CPS problem should be solved by solving hardware security, using hardware to solve hardware problems. So similarly, when we think of solution, software would suppose we do a software-based solution versus hardware-based solution. Okay, so here I discuss attacks, here are the solutions. So software has its own advantage, disadvantage, hardware its own advantage, disadvantage. Potentially hardware has to be there all the time, because hardware has better capability to solve, and software may be used to a certain extent. Okay, so nothing is a foolproof. Software has serious disadvantage of latency. For example, and then software needs a resource to run. You cannot have a software security in a pacemaker or similar devices which do not have computational capability at all. Okay, so the or insulin pump. So you cannot do IoT security with software-based solutions only. So IoT security has more potential for hardware-based. So of course, I agree. Potentially, IT security can be better solved by software-based approaches. Now, when we see the CPS design, okay, we need to solve this multiple objective problem as optimization point of view. That is energy, security, and then this is the AI aspects coming, then the time, okay, then safety, and then the cost, recurrent cost, that is the design cost and the operational cost. So all these have to be optimized. These are very difficult problems, and there are challenges for the design engineers to basically optimize all these things at a time. Okay. Anyway, so then, like if we see right now, quantum computing is coming, okay, and a lot of big companies are essentially competing who will have the first quantum computer. And what is observed, a 2048-bit RS encryption could be hacked by quantum computer in 8 hours. Okay, so that is a serious situation. That means, in theory, that means quantum computers, if they becomes mainstream computing, the existing security mechanism, whatever we have, are meaningless. Okay, it can just like that basically hack or break any security mechanism that we know right now. So that's the security nightmare that we may face, and as a result, people are of course working on different security solutions so that they are ready. So now, this is some set of slides that I have where I discuss how to solve these problems. What is the problem right now we have? That is, we have a multi-object trade-off. Okay, that is energy problem and security problem. All these are there, and how we take all those in account and solve the security problem of cyber physical system. Okay, and the paradigm that I call as hardware assisted security or security by design or secure, they use those terms interchangeably, secure by design. Okay, that is a new paradigm that is evolving. So how that originated? Actually, privacy by design, okay, originated first, okay, because that is how it came from the community. And you might have been aware that is general data protection regulation, GPDR, okay, that European Union put together in 2018. As a result, we did a lot of things as far as I remember. Anyway, so GPDR has a component, privacy by design, and I know the person who really started this privacy by design. Okay, and then we have been thinking, okay, privacy by design came, okay, why not security by design or secure by design? And as a result, we worked with the person who came up with privacy by design, which part of GDPR, okay. And in the March 2020 issue of IEEE Consumer Electronics magazine, that I am the editor-in-chief, okay, we ran a special issue, thematic issue, okay, where we discussed security and privacy by design in more details. So I definitely invite all of you to read the March 2020 issue, which is on security and privacy by design. You will learn much more details of it. So what is here important, and particularly important, the person behind this privacy by design has an article there who discusses much more details of privacy by design, and I have certain things on security by design. Okay, anyway, so the key idea here in the security by design or security by design or privacy by design is work on the security and privacy aspects from the step 0 of the design process. That is the idea. Okay, not you finish the design and see what you can fit for security. Okay, so that means this has to, security and privacy, those have to happen, okay, as a practice in the design flow, okay, starting from the first step. Okay, so that we do not have retrofit the security mechanism, and sometimes the retrofitting may be very difficult. Okay, that's the idea. Okay, so every step think security, that means have the features, you may or may not use it, but have the features, so whenever needed you use. That's the big idea. So there are certain principles that actually the inventor of privacy by design proposed, and I have modified. Actually, I took and modified it for the security approach. And as I said, in the March issue, 2020 issue of Consumer Electronics magazine, we have a lot of details of this. So security has to be proactive, okay, approach. That means you are ready to do things, okay, and it's by default. You need it. That is how. And it has to be embedded to the design. Okay, so as a result, you can basically have a better thing completely integrated with it. Then fully functional and not a zero-sum game. That means we are optimizing all the engineering point of view. That is all the energy, security, safety, all these things, so that we are optimizing in a right way, so that we have a very good design. Then completely life cycle protection has to be there end to end, okay, and then nowhere that is source end to the consumer end, okay, complete end we have complete security mechanism, okay. And remember, we're talking about very big CPS, cyber physical system, not just a single device or a single thing. Okay, and so each device, each software, hardware component, all these things have to be designed with this approach, so as the overall system. Okay, and things should be visible and transparent. Okay, and obviously the user who is using these devices, one should be respecting the users as well. Anyway, so this actually we saw just privacy by design, security by design, or secure by design. All these paradigms like rather recent, and privacy by design has been now well accepted, and it will take some time for security by design to get accepted. But hardware assisted security is one approach that is reasonably accepted by many people, and I have been using these in fact first time in 2006 or 9. Okay, I started using this term in the context of watermarking. So I called hardware assisted watermarking. Okay, and then so which was for IP rights, okay, or data protection, we can say. Okay, so that's the first time I coined, and then I see a lot of people have started using. Okay, so this is essentially because I see the details, so I consider this as a subset of this. So the whatever was thought process here, that is the design process. During the design process, we worry about the security, and that's why I define like this: security provided by hardware, for the system, for the information. Okay, is the hardware assisted security, and I consider this as a subset of security by design. So how the security by design or hardware has is important or significant as compared to the software-based security. Okay, so like software-based security by nature is not foolproof because it needs a hardware, general purpose processor to run it. Okay, let's say you want to run a like a network security and so on. It needs some sort of hardware to run, and they have their own security problems. So the hardware on which the software is running. Okay, and software can be broken. It's a matter of spending time, and further quantum computing time, software security will be further what you can see ineffective. So as a result, that software may not be greatly useful right now. It's not so as in future. So hardware assisted security can have has the potential to provide foolproof solution, and this is a part of secure by design or security by design. And with this theme, I'm running a ACM special issue, ACM Journal of Emerging Technology and Computing, ACM JTC. I invite all of you, whoever are working in this area, to contribute. And if you need more information about the special issue, I'll be happy to provide them. Okay, anyway, so this is a new paradigm. Okay, and when I was reading a little bit, okay, what are the hardware security primitives that we can think of? Okay, so I find that TPM, okay, trusted platform module, is an example we can think as a hardware security paradigm. These are there in many motherboard and so on, and we can use it. So it has its own set of advantage, disadvantage. This is working. Okay, this is used. And then hardware security module, I was trying to build and learn more. So HSM is also used, but these are heavy duty. So that means it is a part of a server and so on, and cannot be used for IoT. This reasonably can be used, or TPM can be used for IoT. And here, another thing I like a trust zone, that is on the ARM hardware and so on. So this has also reasonable capability, but this is, as I know, is more proprietary, that is running in the ARM basically processor and so on. So then POF, that is, I work in this area and also collaborate with Amit on this area. To a certain extent we are using for medical device security. This has a lot of potential. Okay, POF. Why? Because of this is having very minimal overhead. Okay, so HSM, lot of overhead. TPM, not much overhead. Okay, this is reasonable type. This has trust zone is a good combination software and hardware. This has reasonable overhead. But POF is hardware and with a very minimal overhead compared to any of the other solutions. POF has a potential. It has its own disadvantages as well. But energy overhead point of view, area overhead point of view, POF has a lot of potential. So it's a hardware primitive, okay, that generates numbers which can be used for various cryptographic and security applications. That's the idea, okay. And the challenges, that means the input we give generate certain response which is unique to the hardware. That's the big idea. And we do not store this response, okay. That provides the security aspect. Okay, so if you visualize this, it's a hardware module. Okay, it can be a ring oscillator, can be a memory, and can be combination multiplexer and so on. Okay, so POF, various circuits can be used, and given various challenges, generates various response which is unique to this hardware. That's the key idea. Similarly, if different type of different POFs we use, POF1, POF2, and we give same input, it generates different output. So that means the uniqueness, that means this response and challenge, they are unique to a specific hardware. That is what being exploited, okay, to use for different security mechanisms. Okay, so the key idea, it doesn't store, okay, the way we traditionally we store the key and this and that. Okay, we do not store here. Okay, this response is unique to this hardware. That's the big idea. Okay. And the hardware is generating those numbers, okay, that responses here, okay, because of what is underneath nanoelectronic process variation that it has. So this, I was working on this area around 10 years ago. Like several students graduated in this area. I was doing nanoelectronics. So that's I understand the underneath details here. So I remember we are modeling process variation that is coming because of channel length and oxide thickness, all these things. So those basically variations, okay, which are as you can say nanoscale 10 to the power minus 9, okay, those variations which happens because of the manufacturability and so on, okay, so they give rise to variations, and those variations if you capture, okay, as a response, okay, we get basically here the randomness that we are looking for, which can be used in the security mechanisms. That's a big idea, okay. And so essentially semiconductor manufacturing process variation is used as a useful thing for the security applications. That's the idea here. And any topology that we can consider, actually tons of variety of POPs are there, okay. These are ring oscillator based POP that we designed, and then we have very good results, and what is important is the power overhead and speed. Okay, so you can see here microwatt of power and nanosecond kind of speed that we have seen, and they are very suitable for the transportation CPS or healthcare CPS, and we have demonstrated them in practical applications already. And the way blockchain everybody is trying to use everywhere, when something works, people think it can be used anywhere. So like that, POF is being explored to use in many applications. For example, random generator, then you can use it for encryption eventually, device authentication, and memory protection, software licensing, like that, and even hardware ownership and IP right. This can be used. So anyway, so these are things, and so this is a idea that I want to bring to your attention. What is the unique thing here is how secure by design, okay, approach you can follow by going to the drawing board of a system, embedded system we call, or a bigger system. So here what I demonstrated, okay, this was actually a long time ago, but like my students have worked on variety of versions of this, and always people like the variations that we give in this research. So anyway, so here the idea is integrate the security mechanisms, whatever we want, security modules and so on, and then rework on the power budget of individual components. So what is the important point is we add new things, but at the same time we keep the power budget low. Okay, so as less power consuming device it overall it can be. So that's the idea we can consider. That means going to the step 0 of design, taking care of the security, at the same time ensure that power budget is not compromised. So that's the idea. Anyway, so then we have to try obviously different maybe lightweight security, maybe different compression and other things. As a result, you can have that optimization. And here, so we have designed different variations of that. Here we played with the compression engine, and here we have better portable graphics, a different type of better graphics, which is video compression, okay, compared to the original MPEG-4 or H.264. Anyway, so we have done a lot of variety of designs. So as even sensors, ADCs, all these designs we have done to ensure the same thing, that is, as I said, provide security, but do not increase the power budget. That's the big idea. And here, an example is how we go and redesign the healthcare devices, and then as a result, the power budget is very minimal. At the same time, like it provides robust security. So these are different wearable and implantable. Okay, and we integrate POF, which is in our case a very minor power budget. As I was mentioning, we have different type of POF. Here, for example, this is 200 to 219 microwatt, this 250 microwatt. All these POPs are very less per budget, but I'm very happy if we can further reduce, which can happen depending on technology and so on as we keep doing things. So anyway, so then we have corresponding protocol. Okay, what kind of protocol doctor will have when a device is implanted or device is given to the user or the patient, and then when reconfigure, what kind of protocol. So all these we have developed. Okay, this is what we call enrollment process, and this is the device registration procedure. Okay, all these things we have developed. And what is the important point is that we are not storing these responses to this and that. Okay, so we store only server POP challenge. Okay, so this one challenge we store. Okay, rest all are generated on the fly. As a result, there is no security flaw. Okay, people cannot hack. One can only get access if these two POPs are matched with each other. Okay, and accordingly, we have authentication process. Okay, authentication phase. That means a doctor legitimate who wants to reconfigure the pacemaker and so on the medical device, how he or she can do. So this is the procedure that we presented. This is foolproof. We have verified with a lot of different instances, and there is a very good user interface we designed, and overall with a lot of excellent result with the 200 microwatt average power. Okay, a lot of the readings with different data point, and this 64-bit 128-bit key width were experimented. Okay, and this is in the matter of second we are able to verify the security. Now this is I was mentioning yesterday, so as today here in this we have done a lot of things healthcare point of view. Okay, and what is the big picture here is eventually security mechanism. The moment we are talking about insulin pump, it has to have a security mechanism, and then the data, the healthcare data that is going from here, okay, have to be stored somewhere in privacy assured or secure fashion. So this can be done in a cloud storage with certain software, or one can take help of hardware security. But this is more likely hardware, and as a result, we started this work. Okay, this is with MNIT Jaipur with Amit and his students. So they have done amazing work, and this is an example where we have explored arbiter POF. Okay, 64-bit, 120-bit, 256-bit, all these experiments are done, and which essentially this work that we have seen. Okay, here we have POF at the doctor terminal and the edge server at the as well as POF in the devices. Okay, and that's one paradigm we experimented that works with ring oscillator, and this is a arbiter POF based security mechanism, and different POPs and so on, and this also has been validated and working with a high reliability. So a lot more work can be done. This is just a beginning. Okay, and with this we think actually healthcare security problem, healthcare cyber physical system problem can be solved with very minimal overhead. Now, when we talk about, remember I mentioned firmware is an important point, important component. Hardware, firmware, software, all these things are software I do not address. Okay, but hardware and firmware are my interest. Okay, I think software, a lot more work has been done, but solving a software security is not solving CPS security, as I have explained. Okay, hardware needs to be solved, and hardware can security by the help of hardware for the system, for the hardware is the way to go if you want to solve IoT or CPS security problem. So here is like NXP Semiconductor, the solution that how they are validating the firmware, so that, for example, firmware in a electronic control unit of a car, those are serious problems, or a smart grid or smart healthcare also can have similar problems. Okay, that the firmware security needs to maintain, so that we ensure that legitimate firmware is installed in the hardware. Otherwise, the system or the embedded system will behave security compromise is there, and one can take control over it and then get control of bigger systems which is it is a part, for example, like smart grid. Okay, vehicular security, transporter security point of view is a very important problem, and I ran a special issue in November 2019 Consumer Electronics magazine covering this. This is a very important problem, and this work how POF can come to picture to secure electronic control unit is a very interesting idea. Okay, and but long way to go, but at least there are good attempts. And what is important point is we are handling IoT security or CPS security as a IoT or CPS security, not as a IT security. That's the important point that we need to learn from this. So anyway, vehicular security is important, and I like this work here. Vehicular security point of view, and dynamic watermarking has been used. What is the point here? Remember, I was mentioning that is a sensor and actuator. Okay, in a vehicle or autonomous car, the sensor needs to get the actuator needs to get a signal from the authentic sensor. That means which are its sensor which are supposed to give a value to it for next action. But if the actuator gets a signal from a hacker, then catastrophic things can happen. Okay, car can have accidents. Okay, so those things. So that is why this is an idea where the actuator is verifying the sensor data with the help of a dynamic watermarking, and as a result, car security can be maintained. So that's a very difficult problem. I have seen very few work. This is the work that I found. That's why I thought of bringing to your attention. This is an important problem called dynamic watermarking to solve autonomous car security problem. Now, blockchain I was mentioning, long way to go. Okay, we have one of my student, actually rather two of my students are right now working on how to make blockchain useful for IoT domain. It's not straightforward. Okay, blockchain has a lot of problems. So this we were the first people who started paying attention, and we wrote a magazine article. That's why in Ideal Potential, Ideal Potential has a lot more coverage. Actually, it reaches hundreds of thousands of people. So we wrote this. Okay, and that is how blockchain is not ready for IoT, and then we came up with the idea of how we can remove the proof of work from the original blockchain and replace that with something lightweight, and as a result, blockchain works in IoT. That was the big idea, and we have very good results. And in this process, what we said, like blockchain right now, we can classify them as validation type. These are energy hungry. Proof of work is the maximum energy. Then voting based, these are reasonable energy overhead and latency overhead. Then if we use blockchain for authentication, we can completely remove the proof of work and so on, the consistent algorithm, and we can have different set of blockchain altogether. So that is the idea, and we are working. And then in the process, we mentioned that this is where energy consumption happens. This is where a lot of energy consumption happens, and we need to replace this with something. So that's the idea. And first, we proposed proof of authentication, where we do not do the puzzle solving. We do some cryptographic authentication, okay, and as a result, the power consumed here is completely safe. That's the idea, and doesn't need a hardware. A minor essentially, it doesn't need a lot of those. So we can call them as authenticator or trusted node. So we present it. So as a result, we have to go back and change altogether the block structure of the blockchain. Okay, so these are modifications we did. Okay, and as a result, we have different block structure, and then here is the idea of authentication process. Okay, with new blockchain, okay, how and a new authentication with new blockchain without proof of work, like consensus algorithm, how we achieve basically the trust and so on. Okay, we propose ideas. Okay, we define certain trusted nodes. Those trusted nodes in a decentralized fashion are authorized to authenticate on trusted nodes. So that's the idea. Okay, and what we found, these are running excellent. That is, we could verify this running in a Raspberry Pi like platforms, which consume 5 watt of power, as compared to the original blockchain, which is kilowatts of power. Okay, we're running a lot of things. So that is the what you can say, one of the excellent idea with the proof of authentication chain. So we'll be calling this as a easy chain or something we are working on right now. And what we verified, that is this running very fast, okay, with very minimal power. And of course, this has a long way to go if you want to do this, for example, for public chain and other things. But just a good beginning, and one student is right now working. Then we also did another thing, what we call pop chain. In pop chain, what we did, this is we claim that is the first effort where we are integrating pop in blockchain. And what is the job of POF here? Is to provide security, because blockchain is not necessarily secure, and blockchain has a lot of security issues, privacy issues, and so on. So anyway, so we integrated, and this is a architecture that we provided, how we can have POF, okay, integrated in the blockchain, and as a result, the consensus, security, and other things are running through the POF. Okay, so we gave different algorithms for authentication. We call it proof of POF-enabled authentication, or POP, okay, as compared to proof of work that originally proposed. And this is the idea, that is your trusted nodes with the help of POP are doing authentication just in matter of seconds. That's the idea here. And again, we had to do a lot of changes. Block structure we had to change, okay, and a unique block token instead of nonce that it had originally. In the original blockchain, you introduce a concept of unique block token UBT, and then we introduce more information, okay, that is POF ID and so on in this process. And this is the enrollment process. That means when a device comes, okay, and that is how it is enrolled, and then eventually, when access is needed, okay, particularly for medical domain and cyber physical system domain, these are the possibilities. There is a need for a transaction, there is a need for authentication. So we develop protocols that basically can be used for foolproof security. So that means here blockchain, okay, is working. At the same time, the security aspect of blockchain is completely done by POP authentication, which is significant concept at the top of blockchain, which not many researchers have done. So this is a significant result that we published as magazine article for wider usage that came in the March 2020 issue, where you ran the security and privacy by design special issue. So I invite all of you to read more details of that. And we verify this is like security aspect using Scyther tool, and this is perfect. There is no secret flaw that we could encounter at that time. And we have verified with real life hardware. Okay, we had instance a lot of POPs here, then different client and trusted node and all these things are Raspberry Pi model. So this is a mimic of internet of medical things and or in other Internet of Things or cyber physical system we can mimic through this mechanism. And then what we're trying to solve, another kind of problem of blockchain, that is the scalability. Okay, blockchain is not scalable. Blockchain cannot store a lot of data. So we are developing what we call multi-chain. Another student started working on multi-chain. That means we'll decide in the cyber physical system context, we have a lot of devices, we have a lot of data. So how do we do device authentication? How do we keep information of the devices? At the same time, how do we keep information of the data? Okay, so all these things are a much more difficult problem, and blockchain doesn't scale. So we're trying to develop what we call multi-chain, so that different chains we can use. Probably one idea is one chain keeps the data, another chain keeps the devices, or another thinking is completely offload the data storage to a distributed file system like a IPS and so on file systems that is available. Anyway, so this is the research going on, and this is we are very excited, and this is where the second column you can see the original blockchain with that came from Bitcoin, and then we provided a proof of authentication with a different blockchain that is running very well, but we say scalability, that is how much data they can keep. There are still issues. So then actually people are trying. Tangle is another technology which is not exactly blockchain. Tangle technology is available. Hashgraph is another technology available, and we are running a different blockchain, and we have developed a fast algorithm for that blockchain, which is we call as multi-chain or post-blockchain, and we developed the algorithm which we called multi-chain proof of authentication, MAC4 we call it. And this algorithm is authenticating multi-chain, authenticating very fast compared to other algorithms. And then what is important here is the blockchain data structure. That means the blockchain is a data structure where the data is stored, and those data structure we are completely optimizing through with a directed SL graph linked list. Okay, we are optimizing that list so that overall the blockchain that we have is compact. So that can solve the storage scalability problem. That's the big idea here. So we have started, and we have a long way to go, but this is a completely paradigm shift thinking. So here, if you see the summary of a little bit discussion, here we tried to solve this, taking the energy consumed in the consensus we solved, and then here we provided security by using PUF in the blockchain, and here in these this MAC4 and so on, we are trying to improve the storage scalability and so on for the blockchain. So these are like a complete paradigm shift thoughts that we are doing for the blockchain. Okay, anyway, so that means this block structure, which is static in the case of regular blockchain, and blocks are added chronologically one after another. Okay, we are trying to do different. We are calling that a dynamic blockchain. So that means these blocks can be optimized, and overall we have a compact blockchain structure. And again, we have to do a lot of corrections or modification to the block structure. So we added, for example, here we are keeping track of distance of each block from the Genesis block, and as a result, we can optimize, okay, the block structure. So that's the idea here, and we just said we started. We will be continue working. So the results are very promising. Okay, that is, we are able to authenticate in some milliseconds of time, and also the block compaction, that means compact block structure, we are able to get which in a matter of milliseconds of time. And in terms of smart grid security, okay, that is the energy cyber physical system. A lot of problems are there. People are trying, okay, and then one can solve by using the way exactly security and privacy by design. Those things one can definitely introduce here to have, and we haven't done this. Mostly we have so far focused on a healthcare domain, but this is a big domain that smart grid it has, and we will explore these ideas. And in terms of using blockchain, has anybody tried smart grid? Some solutions I'm seeing people have started talking, okay, and probably a lot of blockchains will be used in this domain as well. And this is one work, okay, I was mentioning with the MNIT Jaipur, with Amit and other group, we have done medical domain and so on. And here in the energy sector, I'm working with NIT Rourkela. And this is a very interesting idea that I like, that is how we call it eternal thing. The big idea here is you design a IoT node, and that IoT node is self-powered by solar, and it has security feature. As a result, it's always able to supply its own power and able to be part of a smart agriculture or a smart city kind of environment. That's the big idea here. And this work has been completely, this chip has been fabricated and characterized, and this is actually accepted you can get it in IEEE Explore. Okay. Anyway, and then we are second variation of this. We are working what we call as Eternal Thing 2.0, where we are adding like a Trojan resilience mechanism compared to the POP mechanism that we have here. Okay, as another design paradigm. So anyway, so we have the chip, and we are waiting for its characterization to basically submit. Anyway, and I was mentioning to you that is data like system and other things, device, all these are equally important secret feature. So that is why we are basically this work, that is how we can have different edge server with security mechanisms so that we can have balanced data across the CPS and the security is well maintained, and then potentially blockchain running on this edge data center. That's the idea. Okay, so under this idea, we basically published this article, which is very well read, and this is very unique idea we have. That is how these edge data centers have proper load balancing and providing security. Anyway, and a very basic simple thing I wanted to mention here, this figure, that is, okay, we're talking all big things, okay, no doubt, but we should not forget at the end, each data needs to be protected, okay, system needs to be protected, device needs to be protected, data everywhere needs to be protected, and we can protect them using hardware software mechanisms, okay, and there is an example is a hard drive or USB with a hardware encryption mechanism. And this is essentially our hard drive storage or the non-volatile or permanent storage protection. But at the same time, in the embedded systems, okay, the memory, that is basically the SRAM, that means the cache, okay, where the computation happens, those need to be protected as well. Otherwise, one can get information from there. So those can be done, and we have tried some algorithms. Okay, and this is a very good embedded system people point of view, like how we can protect the memory. And with this idea, we had encryption decryption modules running at the top of cache and to protect even during computation all the information. And we had also done certain work that is on the side channel resilience, okay, and a lot of people are working, but we did a long time ago. This work I wanted to bring to your attention. It has still a lot of potential to work in this area because I was mentioning that is encryption can be defeated by DPA, or that is differential power analysis or correlated power analysis, very easily instead of defeating the encryption algorithm. Okay, so from the security by design point of view, okay, and we know now any smart system we are talking about will have AI. Okay, so a good trade-off of security and AI is needed, and that trade-off differs whether we are optimizing at the end. That means whether we are optimizing the security of our wearable and the intelligence that it can provide or implantable, or the security of the edge or a router at our home. Okay, we are optimizing that. Okay, or we are optimizing the security and energy in the cloud. It has here, it can have much bigger resource, and as a result, a lot more heavy duty security and a lot more intelligence can be provided here. So these are different trade-offs one has to have at different nodes in the overall CPS paradigm, and then only we can have a foolproof secure by design approach solving the different layers of the CPS. And in a bigger CPS, definitely this is 101, access control point of view, all these things, okay, variety of what is the key message I'm providing here. That is, instead of just counting on encryption to provide security, okay, how we can have variety of things, okay, like here medical signals, ECGs and EEGs, all these, even finger vein, all these things are part of security mechanism. As a result, what can happen potentially is we are less dependent on the encryption kind of mechanism, which are potentially what you can say resource demanding in themselves, are slow and may not be able to useful all the time on all IoT and CPS domain. So these are things that may potentially be used as different paradigm for security. Okay, so with this idea, we worked on NFC security, that is near field communication, and this security we developed a new card. Okay, we call it SwingPay. In this card, we provided biometric security, which is like a credit card or identity card, whatever you can use for. And this is we developed the protocol. If we were using this as a credit card, what are the payer module, pay module, all these protocols, and then so this is a foolproof security mechanism in a credit card kind of thing where biometric is used. That's the idea here. Similarly, people are trying for RFID. Okay, this is NFC. I mentioned the previous one. This is RFID. Okay, these are some simple solutions. As of now, when we have a RFID device, for example, my passport, we keep it like this. Okay, but in a bigger context, we have to have certain design paradigm, which I haven't seen, we have not done as well, where we go back to the RFID, the way exactly here NFC card design paradigm we went, we built it here. Similarly, how we can go to RFID completely step 0 of the design process and add secret feature, that is people can try. I'm just bringing it to your attention. So anyway, so all these things when we have to consider when we are designing the overall CPS, the intelligent aspect of the machine learning aspect, so that we maintain the trade-off as consistent with what I've been saying here. That is, in a secure by design approach, security and other other characteristics of the CPS needs to be taken into account together, so that we have low overhead security design. That's the point. So anyway, so these things we have to think about the intelligence when dealing with the security. And when we are dealing with the security and intelligence together, data is very important. Okay, so how to have good data so that the data is real. Okay, like this, not like this, which is looks like real, but it is not. So anyway, so important data, getting right data is important. Okay, and I also want to mention here that is fake data may give us bad models. Okay, and fake hardware may give us very bad systems. Okay, which can be hacked easily. Okay, so here particularly the right bottom, that is car issues. Okay, the embedded hardwares. Okay, that I consider as a very serious thing. For example, you have an issue which puts, let us say, automatic brake for your car. Okay, and then that issue is bad issue, fake issue. Then what happens? Your brake may not work. Okay, that's the life-threatening situation. Okay, so that I wanted to bring to your attention. And these kind of problems here, right side hardware problems can happen if you have a compromised firmware or a reverse engineered hardware. Okay, all these can eventually lead to these kind of problems. Okay, so people, those who develop model and develop AI from the data, some people are advocating, okay, if fake data is able to train a model, why don't you use fake data to train a model? Okay, so EIC of Conservatory Magazine, who was before me, is Peter Corcoran from Ireland. So this is his slide. Okay, so he says, okay, why don't you use fake data, which may be cheaper? Data is money. Okay, data is new gold, a lot of people say. So why don't you use that? Okay, but people have their own thoughts. I just wanted to bring it attention that data is important for AI. Okay, and how we get the right data so that we have right model, that is critical. And AI and security needs to be work together so that overall CPS is a very good CPS. Okay, and I have also mentioned how AI can have its own security issues, particularly important in the context of autonomous vehicles. Okay, so anyway, so that is why I was thinking that is data, we need to completely see the life cycle of the data, where the data originates and where it is modeled. So those whole life cycle you have to see, and we need to probably have a certain kind of framework so that from the source to destination end, everywhere we have some level of protection. Okay, so maybe that is why, so I call this as secure data curation. That means you take the data, raw data, and curation means it's like keeping the data in a proper way so that it can be used. Okay, so anyway, so filtering, aggregation, all these things. So any step, okay, how we can do it in a framework where data is never compromised. So that's the idea. But anyway, this is just as a question I put. People can think that way. Secure data curation. I just coined the term. Okay, and then other security aspect I was mentioning, ownership is a very important aspect. Okay, media, that is a movie and other things. So as a hardware, okay, are important that one can think of. I just not go to the details. Okay, and so this, in fact, I developed a long time ago. This data related, and then also these things we have some works. Okay, and this is the hardware that I gave long time ago, which is considered as the first low power watermarking chip. Okay, that is a watermark chip we designed, which consumes 0.3 milliwatt power that went to the part of camera and so on. That's a very significant work. And a lot of people have been motivated by those things. And here is an example from this is from Austria who use these ideas. Okay, and this is another sensor-based watermarking. This is from Canada. They have also used the watermarking ideas that I gave. Anyway, so with this, we have basically we covered a big spectrum of cyber physical system or Internet of Things, so security by design, how we can use those to make foolproof. Anyway, so security privacy related are important problems that we know. We have extensively discussed that. And data, device, yes, AI, all these need to be secured. Okay, we can have software, hardware-based solutions. Hardware have its own set of advantages, low overhead primarily, and then it goes well with the design flow. Okay, and what is security by design? The key factor is simple: is no retrofitting, please. Simple. Okay, that means you make this as a design flow so that we do not retrofit. And a lot of this is just a beginning. Okay, privacy by design came first, then security by design is just getting attention. So a lot more work can be done, and those paradigms is wide open to be used in the healthcare domain, then energy, then or transportation, all these domains. And overall, okay, this sustainable IoT and other things that we get can build sustainable smart cities. That's the big picture. So with this, I thank you for your patience. It's a long talk. I was given 2 hours. Hopefully, I covered quite a bit, and I'm ready to take in questions.
Okay, thank you, sir. So I think we have one question from Gaurav. Yes, Gaurav, unmute your mic and you can ask your question.
Hello.
Yes.
Yeah, hi, sir. There's this thing where we talked towards the end that data is the new gold.
Mm-hmm.
So in something like health cyber physical system, I mean,
Yes.
Tomorrow a big player may come in like Google, Facebook, or even our own India's Geo, and they may offer something like to the healthcare providers or even to the health medical device manufacturers that you give us the data, like you give us the reports generated by the patients, and in exchange we are going to drive the prices down of the test and everything. Like let's say a blood test which normally costs $100, they are going to come in and say it's going to be for $25, and just in return that you need to give us the blood reports. So we are going to drive the advertising, like we are going to give all those extra advertising to the patients, like new services, maybe even insurance and things like that. So is this like this comes more, this is not really a security issue, but this comes more as a ethical and privacy thing.
Exactly. Right.
So my question is, one, is this a concern for you as an engineer? And two, if it is there a solution to it beyond laws? Like, is there a technological solution to it?
Okay, it's an excellent question. Okay, so this is definitely, I don't think, first of all, in the US healthcare sector, I can tell they cannot take data easily. Okay, this is personal privacy issues. The HIPAA, that is Healthcare Privacy Act, is there. HIPAA, HIPAA is there, and they cannot just like that take the data. Okay, that is first. And second, your question is excellent as an engineering perspective. Okay, engineering perspective, if I see, so that's the legal perspective. Okay, privacy they cannot take. Okay, and then engineering perspective, suppose they want to take the data, there has to be a privacy solution. Okay, so there are solutions. They call it anonymization. That means, let's say a whole city data, okay, with million population, okay, is there, and the data, how they make that those data anonymous, okay, so that whose data is what. Let's say person A, height is 5 feet 5 inch, weight is this, and these are the health records. Those identification cannot happen. Okay, so anonymization or other things, those are methods available. Okay, and sometimes this overall big city data and other things are needed to be processed. Okay, but they are authorized people. For example, state of Rajasthan wants to process the data so that it can keep track of the health problems of the state. Okay, that's a different reason, and that state government takes that and makes the data anonymous and processes. That means how many problems, how many citizens have what kind of health problem. Or a city mayor takes the data, okay, and processes what are the health problems of citizens living in that specific city, so that they can accordingly design the hospital. Okay, so those are like epidemiology also point of view. Right now, for example, we are maintaining the pandemic, which city has what kind of COVID-19 infection and so on. So those are data some may compromised. Okay, but those are essentially going through a specific protocol by the government agency and so on. Okay, so those are different reasons happening. But in general, unless a pandemic like serious situation, data will not go where the direct person is identified. Okay, and engineering point of view, there are private solution available where all these identification, de-identification, and all these things happens, and then it can be used for the purpose that is intended. As I said, epidemiology, or you want to make a plan, what kind of hospital is needed in a city, how many beds are needed, those kind of planning purposes, where it's all made anonymous. That is, somewhere names are removed or data is shuffled. Okay, let's say instead of writing 1, 2, 3 alphabetically, some shuffling and other things are done, so that from the data one cannot correlate who are the citizens. Okay.
Yeah, sir. So the onus for anonymity is on, if I understand correctly, is on the cloud department.
Exactly. So the whoever is the IoT cloud, okay, or the CPU, the cloud server, okay, they are the ones who will. So there are algorithms available. That is privacy. That's why now, like, even though a lot of people are worrying for security, privacy. That is why it has a lot of demand as well, because of these reasons. Okay, how to, particularly in US, it's even in US, okay, even my spouse cannot see my data, healthcare data, unless I give the consent. Okay, that's why this is much more serious problem. So that's why there are private solutions and other solutions are being explored. A lot of solutions are available, and it's always people want to get better solutions, but they are there.
Okay. Thank you, sir.
Okay, thank you.
Okay. So, any further question? So,
Somebody, okay, yeah.
So sir, actually means you have touched upon very sensitive topic for a security, for a IoT and CPS, because particularly I see in India, because people are not getting a trust still in this such kind of security, especially in a Bitcoin or maybe in a telemedicine, because basically they are not accepting such kind of technology because of the some security vulnerability is there. Okay, but
Right.
sir, when I talk about the security, then as a researcher probably I would like to have a security, then I will add more and more layer to have a more robustness, but at the same time I need to worry about the energy also. Okay, so
Exactly.
as a researcher, for me it is very difficult to know which comes first, whether I need to look for a security or maybe I need to worry about the energy at the same time. So sir,
Right.
what smart solution we have to think about that, whether maybe energy or security?
Okay, so both, that's why this paradigm, that is security by design, whatever has been coined, that's the motivation. Okay, we cannot say, oh, I'll make the most heavy duty security, but it may not run. Okay, it can drain the battery in no time. So that is why the trade-off has to be there. Energy obviously is important, otherwise how the device will run. Okay, so we cannot have a security and drain all the battery. Okay, so that is why this paradigm, what I mentioned as security by design, is very important, where we think the energy aspect, the intelligence aspect, as well as security aspect as a trade-off. Okay, in fact, the original inventors of privacy by design, they say you do all these things at the same time, you do a better job of all those. That means you have more security, you are doing a low power design, and also you are making intelligence, which is impossible as engineering point of view. Okay, but that is what original people's goal. But that's why I bring it down a little bit less expectation. That I say That is, we have to have energy and intelligence. I called ESR trade-off. Okay, that is energy, security, and response. Response means AI and its decision. Okay, ESR trade-off. That's why I called. Okay, we have to have those, not just security by design in a traditional way, the way originally invented. That is not have a zero-sum game. That means you win on everything. That is engineering impossibility. That's why we have to have a trade-off. Okay, some security provided, so that some overhead on the energy, and then some intelligence provided, so some overhead. So that's the trade-off. Okay, but it's a difficult problem, definitely.
Okay.
That's a POP we have done. POP is a very good. It has a lot of promise. Okay,
Yes.
even though I myself can give counter example. Okay, that POP may not work certain scenarios, but at least it's solving the energy aspect. Okay, doing very fast and less energy overhead and some security.
Yes. Okay. Thank you, sir. So,
Sure.
is there
Thank
any
you.
further question? I don't see any. So presently there is no, but there are very much active participants in the YouTube also, but because of some
No, no
reason
problem. So yeah,
they are not
tell
able to
people.
interact with us. But probably they can contact you, sir, for through
Yeah,
mail if they have
through
any.
email, and maybe let's hope next year or so I'll be able to travel.
Yes, yeah, definitely. We would be happy to host you, sir, over here.
Sure, sure. Yeah, we'll see. Okay,
Okay.
thank you, everybody.
Okay. Thank you. Thank you, sir.
Sure, sure.
Good night,
Thanks.
sir.
Good night.